to have today's Infosys Condensed Matter seminar. So many of you already know that this Condensed Matter Visitors Program is kind of new at TIFR, and it's supported by an endowment from the Infosys Foundation. And it's a great pleasure to have Professor Philip Kim. He gave a public lecture yesterday, which was really very nice. Even for the people who in the field, it was very insightful. Today he's, of course, going to talk about slightly more detailed physics, an exciting physics that goes on in his lab. Let me say a little bit about him. Everybody kind of knows him. He's done some really pioneering and fundamental contributions in a lot of different aspects of physics, starting from heat transport, which is still his continuing interest, looking at mesoscopic systems, particularly his contributions looking at 2D materials, starting from graphene, now looking at more complex aspects. Interaction physics in 2D materials is quite amazing and exciting for the people in the community. He got his PhD at Harvard, where he did work with Professor Charlie Lieber, working on carbon nanotubes, and then he did his postdoc at Berkeley, working as a Miller Fellow, I guess primarily working with Paul McEwen. Then after that he was a professor at Columbia for many years, and where he did sort of really the early work on graphene, which the community kind of values. And over the last 3.5 years, he's been professor of physics and applied physics at Harvard, where he's kind of continuing some of the exciting work. So it's really a great pleasure, Philip.
Thank you, Mandar, again. Well, thanks again. So thanks for also coming. Those of you again was yesterday. I hope that I can give you a little bit more detailed stories, the continuing stories from the yesterday's general introduction of the 2D materials. So I'm going to talk about a bit of more detailed stories, and especially hopefully that some of the ongoing work rather than kind of published work. So we'll try to give you some sense that where we are in terms of the field and where we are going. Right. Let me start with thank my collaborators who actually make this work possible. So I will just kind of give you probably about 3 pieces of the stories that basically the 3 groups of the people who are responsible. The first part of the story is about the magnetic excitances in the graphene and magnetic excitant condensations. And then second part and the third part is related with the transition metal dichalcogenide at TMDCs. The quantum confinement was carried by the Kawang, and Intellect Extens as basically a team of these 3 people, Luis, Andy, and Kate, are responsible. But also this is done by the very strong collaboration with the other people in the Harvard as well as other places. Optical spectroscopies, which is an important part of the Intellect Extens, was in collaboration with the Hong Kong Park's group and Michelle Lukin's group of these talented postdocs and students. We have quite strong theory background, the support that Eugene Damler, Bert Halperin, and that their students actually help us understanding a lot of interesting things going on in the directions. And finally, in terms of the magnetic excitant, there's our competitions and collaborators as well. The GLE and the Corridin at Columbia was quite responsible. And then, as usual on the 2D community, boron nitride is a very important source of the material or important ingredient of materials. It was provided by the Taniguchi and Watanabe and NIMS in Japan. Right. I actually showed you this slide yesterday, and idea is there's a new era of this material science or material physics that rely on the two-dimensional, so-called two-dimensional materials. The nature has given us that the various layered materials where that all the chemical bond is within the layer, while that between atomic layers, weak van der Waals force hold them together. Hence the name of the van der Waals material comes from. But there, the key important part is since all the chemical bond is within the atomic layer, in principle, this atomic layer can be extracted or grown, whatever method, but isolated atomic layer is possible, and they are stable. moreover, they comes with a various different flavor, like the semiconductors, superconductors, and those kind of flavor, and such that in principle you can stack them together. And when you stack them by designing, you can actually provide some of the functionality, like the Lego blocks, that you can just take this couple of the Lego blocks with their functionality and just kind of place them together, make the three-dimensional structures, and those kind of thing has been possible, right? And briefly mentioned, there are a lot of the excitement of the also in application side, based on this type of the 2D materials as a Lego blocks and building up some of the functional structures for the devices. So now today I'm going to focus on of the physics, and especially electronic and optoelectronic physics. And I want to confine myself into some subset of the two-dimensional materials. And that here the list of the material I'm going to discuss is monolayer and bilayer graphene. This is a the typical two-dimensional system we start with. One of them becomes Dirac fermions, and the other one is chiral fermions. And I don't want to kind of dwell on a lot of languages, but basically these materials do not have the gap, but then there's a unique vary phase type of structures one can rely on. Boron nitride is very similar to the graphene, except that 2 carbon atoms in unit cell is replaced by nitrogen and boron, such that you break the inversion symmetry of the nice inversion symmetry of the monolayer graphene. That immediately open up the gap, such that the ionicity of this lattice provide this boron nitride is a good insulator, as well as high quality crystal often comes around. Boron nitride serves as a good substrate as well as a dielectric, right? So here that another set of materials that briefly mentioned yesterday called the transition metal dichalcogenide. It is a rather complicated system. In the unit cell basically consists of say 2 sulfur atoms or seleniums or tellurium atom, what we call the chalcogen atoms, and 1 transition metal. And all these materials are relatively heavy elements compared with carbon and boron and nitrogen. So you can immediately see that they have the strong spin-orbit couplings, and that will provide that the band structure is rather uniquely different from other materials I just tell you. Although in terms of the projected two-dimensional, the crystal structure is very similar, in some sense it looks like the boron nitride, right? Therefore that inversion symmetry is broken to open up the gap. On the top of that, they have the strong spin-orbit coupling, which will make this band split in the spins. And moreover, considering this time reversal symmetry in the system, then you can see that the spins and the valleys are coupled together in a sense that spin is polarized one of the valley in this two-dimensional Bilayer zone, but then opposite valley has the opposite side of the spin sense. So there's intriguing that part of this spin valley locking often plays quite important role to understand that the physics going on these TMDC 2D materials, right? So idea there is basically that combining all of these 2D materials try to make some of these functional structures, right? Immediately you can see that, especially when you're just thinking about the various different semiconductors available by just combining this TMDC with the different metals or different chalcogen atoms. You can think about making the heterostructures with various different type of the band structures is possible immediately. So borrowing some simple idea coming from semiconductor heterostructures, you can immediately see that there are something that we can build up out of this combination of materials, right? So that will give us enough motivations that one can just work on this type of materials. Now, it's not only just motivation or PowerPoint demonstration of the stacking up these materials. Indeed, one can stack these materials. So this is also a slide I showed you yesterday. But if you just go for a little bit detail, this is a method developed at collaboration that I had at Columbia University, especially Jim Hon's group is really responsible for the come up with this nice method. The method works that you break these crystals down to the monoatomic layer, and then using the particular van der Waals materials like the boron nitride, for example, and using the polymer to just kind of pick up this boron nitride, and then you can just pick up the materials successively one by one, that just controlling the adhesion force between this layer by just controlling the temperature of this substrate or the polymer stages. But in the end of the day, you can get the stacks of these 2D materials. In this particular example, it is boron nitride or graphene encapsulated in between boron nitride can be made or synthesized in such a way, right? In the proper condition that you get a few tens of microns or at least a few microns of the crystal areas is extremely clean. And if you just cut it through the the cross-sectional TM image, you can see that this atomic interface is extremely clean, indicating that we can in principle make these materials or the heterostructures one by one into by the designing. Another important aspect of this heterostructure is you can also cut these heterostructures by etching, especially if you design the etching recipe well, and you can just etch certain materials preferred to another material, exposing the other materials. And this type of the etching techniques after the heterostructure allows us to make the contact on all of the individual atomic layer. Especially when it goes with the graphene, we know that how to make the really good contact on graphene by selectively etch away the boron nitride and make this direct coupling onto the metal to the graphene layer throughout this sigma bond and pi band network, right? If you just choose proper metal conditions, it has been demonstrated one can make the extremely good contact onto this edge of the sample through the graphene. And all these things that in combination with the good boron nitride encapsulations and high quality contacts, you can make the device out of the graphene encapsulated boron nitride extremely high quality, such that if you measure the mean free path on those kind of samples, mean free path is only limited by size of the graphene sample, right? So if I have about 10 micron size of sample, basically mean free path is about 10 micron. And this tells us that the sample becomes completely ballistic and such that you can realize a lot of interesting quantum transport measurement in this kind of system. So right now, I think people have been demonstrated this off-Shetter's butterfly or this fractional quantum effect or just the combination of those kind of things happen. So if you're interested in deep into this quantum transport measurement, the graphene is a good vehicle that one can realize a lot of interesting part of the physics. I'm not going to dwell on anything today, but at least this shows us where we are and where we are going in terms of high quality graphene sample, that if you're interested in the interacting physics in there, there are a lot of rooms that one can still explore, right? But beyond the graphene, very similar technique has been demonstrated to make these interesting samples, right? Or reasonably high quality samples. So this is case that instead of graphene, now we have this the moly disulfide encapsulated in between this the boron nitride. Try to get the high enough quality. Again, here in this particular case, we can stack them together with the graphene, where a few layers of the graphene act like the good electrode to make this good contact on boron nitride. The collaboration that we had with again, Jim Hon's group demonstrate that in such encapsulated TMDC semiconductor crystals show decent quality. It is not as high as graphene, but mobility-wise, it's something like thousands, 10,000s of mobility can be achieved by the encapsulating the TMDC in between the boron nitride. And in this particular moly disulfide case, making the contact with the graphene make the reasonable contact such that you can see that this quantum oscillation in the sample, right? Now, this type of things can be expanded in not only moly disulfide, but other semiconductor. Moly disulfide is N-type semiconductor. Tungsten diselenide is a good P-type semiconductor. Of course, when you go into the P versus N-type semiconductor, you have to come up with a different way of making the ohmic contact. We found that by controlling the thickness of the metal electrode, in this particular case is platinum electrode, simply changing the thickness of the platinum electrode, we find that you can tune the work functions a little bit. We don't know exactly why, but at least phenomenologically, if you measure the photo emissions spectroscopy, we know that we can change this work function of platinum electrode by controlling its thicknesses. And once you match its work function with the work function of this Van der Waals system, even for this P-type semiconductor of tungsten diselenide, you can stamping onto the pre-made electrode and encapsulate with boron nitride. You can get the decent contact quality and high enough to mobility such that you can get the quantum oscillation under the magnetic field where the quantum effect start to appears in this type of system. So we know that it's a decent quality. Compared with graphene, it's much inferior, but mobility is several thousands to the 10,000s of mobility is available, and you can encapsulate to make the high enough quality device where the quantum transport is possible. So we know that now semiconductors is also in our hand, and then you can start kind of develop the many devices, right? For example, here is tunneling diode. One can create it between two basically tungsten diselenide samples that the one layer and the other layer, and put this two layer of the boron nitride in between. This make the basically good tunneling diode or tunneling transistors, which can be controlled by the gate voltage and top and bottom. So one of this top layer turn into P, and the other one is N-type by just controlling the gate voltage, for example, and create this tunneling diode, where that if you just look at this the IV characteristic, bias voltage versus current, that given gate voltage, you can see the current increases and shows that this the peak behavior and increase again. And this is often what you call the NDR, negative differential resistance, often comes from this tunneling behavior. And if you just look at the details, this NDR behavior can be tuned by the gate voltage as well. Tells us that indeed it's spatial, this gate, the band alignment is important. If you look at a little bit detail, basically this is based on the resonance tunneling, where the 2D momentum conservation is important, and that's why that we got this type of the NDR effect. Okay, this is not the deep physics, but at least that it starts to demonstrate we can build up the functional device based on this Van der Waals stacking and making reasonable contact. Now let's kind of go one step further. Just try to kind of bring it to the really quantum regime. Now, once you have this semiconductor, especially 2D semiconductor, there are a whole slew of the techniques we can apply to make the so-called quantum devices. A lot of cases in the two-dimensional electron gas, people know how to create these confined structures by designing these local top gates, right? If you look at the high-quality